Hello and welcome. This is Taimur, your host at IEEE Young Professional webinar series. I am representing Vehicular Technology Society in the Young Professionals community. And here today we have Professor B.K. Lau. He is actually one of my professor during my master's and PhD studies. And I have honor to study and learn from him. And he is one of the experts in antenna technologies, working for last few decades. He has industrial as well as academic experience. I will not take too much of the time, and I would like to ask Vincent to introduce himself. And welcome, Vincent.
Thank you, Taimo.
So glad to have you here.
I'm glad to be here.
Yeah.
So thank you for inviting me, and I want to also thank VT Society for the privilege to give a talk on massive MIMO. So as Taimo has said, I'm from Lund University, and some of you may have heard that at Lund we have been doing a lot of work on massive MIMO. And massive MIMO is important as a technology because it is a key enabler for 5G systems. So among other 5G capabilities, it is intended to support high mobility, right? So this is of interest, especially to VT Society. Another major aspect of 5G, which is relevant to vehicular technology, is cellular V2X, which can enable connected cars to a very large extent. So looking at the title, some of you may have a few questions coming out of your mind. For example, what is massive MIMO? For those of you who have not heard of it, I know that everyone would have heard of 5G, but maybe not everyone is aware of what massive MIMO is, or at least not the details of what it represents and how it works. And why do I refer to massive MIMO as a beast? And how do we tame this massive MIMO beast? Before I answer these questions progressively in my presentations, I want to start by commenting that massive MIMO is a cellular base station technology for 5G. And massive MIMO has a lot to do with base station antennas. So base station antennas, which are placed on masts or towers, is a common sight. I think we can relate to sight of such huge towers, and they have among them base station antennas mounted on them. And we have these rooftop versions, which are smaller. They're basically is supported by a much smaller beam. And then you can have in the suburbs such sites of metal base station towers with the equipment that is down here in a smaller shade. So these columns here is where the antennas are located. And I would like to show you what these columns look like. I guess not everyone knows what is inside these columns. So inside these columns are the antennas. So here we have a traditional 2G GSM base station antenna, where you can see that these elements here, these antenna elements here, are of two different sizes. Now, these two different sizes represents the different frequencies of operation. So this one, for example, is a GSM dual band antenna. The larger ones will be for the lower band, and the smaller ones will be for the higher band. And then we move on to 3G and 3.5G of LTE base station antennas. Then we have in these columns, which can look quite similar, but they have more antennas. Now, in these LTE systems, you have more than one antenna operating at a given frequency band. So here you have 4 ports, one for the low band, one pair of antennas for the low band, and one pair for the high band. And then comes the 4G, or we call it LTE Advanced. And in such systems, the antennas consist of many more ports. So especially that they allowed for 8 transmit, 8 receive antenna configurations. And that's why you can see that these antennas are bigger and they have a lot more output ports. And these columns get even bigger for 5G. On this slide, I show you some prototype 5G antennas from different base station providers or equipment providers, including ZTE, Nokia, and Ericsson. So essentially, from 2G to 5G, we start off having a 2G system with just one antenna, and these are more than one element, but they are connected to one port to often to increase the antenna gain and having the possibility to have electronic tilt of the antenna as well. And then you have the 2 transmit to receive, or 2 ports per band. So in each low or high band, you have 2 ports. And in order to save space, that you don't have to put 2 antennas side by side with some distance in between, often you use polarization diversity. So you have a plus minus 45. Of course, the other way you can have it is having a vertical polarization and a horizontal, but then you have often imbalance of power due to channel characteristics. So with this plus minus 45, you get 2 antennas. And as again, these of the same polarizations are connected together often. And here you have 4 consisting of 2 cross-polarized or orthogonal polarizations of plus minus 45 and another column here. So this is relying on both polarization diversity and as well as spatial diversity. So with this, you have also a transmit and receive. And here you can see an example where you have in some bands 8 ports being supported for one frequency band. And then you have 5G, many more ports. Here it is a version with 64 transmit, 64 receive. And these dotted or dashed line here represents only 2 ports, because these 2 of the same polarizations is connected to one port, and these 2 of the other polarizations is connected to the other port. So here we notice very clearly that the 5G antennas are of many more elements. And why is that? To understand this, I would like to bring you back to some basics on MIMO, and then talk about multi-user MIMO. And with that, I can explain to you what massive MIMO is all about and why we should design these antennas in the way that we want to. So what is MIMO? MIMO is multiple input, multiple output. So basically, it means that we have, in general, more than one antenna at the transmit side and more than one antenna at the receive side. Simple example is 2x2 MIMO systems. This is basically the phone I have right now. This, of course, is not the real antennas, just showing it for the illustration that if I have a 2x2 MIMO system, then there are 2 antennas. In reality, these antennas are inside the phone at my terminal, and 2 antennas at the base station sites, as being shown here. And MIMO system is very special because it is able to provide better performance in the presence of multipath. Multipath means that the signal from the transmit to the receive side does not only go through the direct path, but goes through other reflective parts, diffracted parts, and so on. So this is why MIMO is very interesting, because it is exactly the kind of environment that the cellular system provides. So it works very well in the cellular environment. But what is so exciting about MIMO? So MIMO, essentially, it provides ideally a data rate that is increasing proportionally to the number of antennas that you have. So one can run some simulations. And of course, these simulations have also been verified in measurements with real channel data. So for simplicity, I just show you what would be the case when you increase the number of antennas that you have on both the transmit and receive side. So this is the number of antennas you have on both the transmit and receive side. So for the case of 1 by 1, it is SISO system, the conventional system that we have. And on the y-axis, I show you what is the ideal data rate that we can have, the ideal average data rate, because these have to be run over random realizations of the channel, right? You don't run only one snapshot of the channel, but over multiple snapshots of the channel. So if we look at this, you can see clearly what I said earlier, that the data rate can increase proportionally with the number of antennas. So if you have 5 by 5 MIMO system, you can get 5 times the data rate as you would have for the 1 by 1 system. Now, what is very special about MIMO is that you don't even need channel knowledge at the transmitter. So without channel knowledge at the transmitter, you can get this linear proportional increase in data rates with the number of antennas. And what is even more important is to keep in mind that when I have there more antennas, I'm not increasing the total transmit power, because essentially what I do is that I divide the number of antennas, the power by the number of antennas. So it's still the same total power, but you get this linear increase in capacity or the data rate. And here, capacity is expressed in terms of per hertz. So I'm not using more spectral resource. And this is why MIMO becomes so popular in the early days, because spectrum has become prohibitively expensive. It's very so expensive that it was billions and billions of dollars. And if one can get more spectral efficiency, then one can gain a lot, right? It makes a very good business case. So for those of you who are interested to reproduce this, you can basically take the MATLAB script that I have written here. Okay, so MIMO at first was meant for a single user system, meaning that the MIMO is for one base station transmitting to one user. There is not more than one user in this configuration. But quickly, people recognize that we should use MIMO to support multi-user. So instead of base station of 2 antennas with user of 2 antennas, then we can trade that to 2 users each with 1 antenna. And it will still work very well, right? There is a need to change some of algorithms because the situation has changed slightly. For example, the collaboration between these 2 users is not so convenient anymore. So this is called space division multiple access. We are able to use space as another resource to provide multiple access. Now, so this is multi-user MIMO. And what is massive MIMO then? Now, multi-user MIMO means that 2 antennas at the base station can support 2 users, each with 1 antenna. And theoretically speaking, K base station antennas can, by the same means, support K users. The problem is that the complexity of the transceiver to support this multi-user MIMO becomes impractical. It becomes too complicated. So this is where massive MIMO comes in, right? Massive MIMO basically is named mainly, I think, after the fact that you need to have very many antenna elements. So by having very many antenna elements, M, much greater than the number of users, it allows us to get very good performance near to the optimal that we can expect with very simple processing. So going from 4G MIMO system, which is mainly single user MIMO, to 5G MIMO systems, we have changed some one fundamental fact. In the 4G systems, it was single user, and therefore we need to schedule different users in different time frequency resource, right? So in OFDM, you can have different time frequency resource. In 5G, you are able, in addition to time frequency resource, you can schedule the user according to a spatial resource, right? So now you can have individual beams almost to each user. Of course, in a real multipath environment, it is not as simple as this very clean line of sight beam, but it is just for the sake of illustration. So very many antennas enable us to get very good multi-user MIMO performance with less complexity. And complexity is such an important issue in practical implementation, and this is why massive MIMO is so favorable among those who want to use this technology. So massive MIMO really works. So this was a news release from Ericsson about a week ago that it is accelerating a 5G mid-band rollout of ultralight massive MIMO solution. So this ultralight solution is a panel which I can show you. It weighs about 20 kilos. It can have 64 massive MIMO antennas together with the radio. So it is going on right now, and a lot of things is happening here. And of course, consumers can feel the impact by the better performance that the massive MIMO can afford. So let me move on now to massive MIMO antennas. So massive MIMO is a lot about having very many antenna elements to provide the massive MIMO behavior. So the first massive MIMO antennas that were used were not actually built for that. It was ready-made channel sounder antennas. Because for channel sounders, you actually need very many antennas in order to measure and characterize and thereafter model the channel. So here we have the cylindrical array. We can have 128 elements altogether around this cylindrical antenna array. And the other array that is used is a virtual one, where we have one antenna element that is moved 128 times to 128 different positions, right? And most of these are set to have half-wave element spacing. So these antennas were, at the time, used mainly to verify the very promising theoretical and simulation performance. So the experimental work that relies on these antennas and, of course, the channel sounder has been able to verify the theoretical and simulation performance. So it was actually a very good start to the massive MIMO research. And then a few years later, Lund University started to build a testbed antenna. It's called Lund Massive MIMO Testbed Antenna, to MaMI. And the testbed looks like this. The antenna is this panel in front. It's connected, well, at least 100 of the ports can be connected to 100 radio chain provided by 50 USRPs that is mounted on the racks. And of course, then you have clock distributions and other components that are needed as well to support this. So the testbed array, which consists of this panel, is basically made of dual polarized patch elements. There are just very many of them, and they are arranged in a T-shaped structure, and all of them includes 320 ports or 260 dual polarized elements. This patch array was designed by my former PhD students, Dr. Zach Myers. It has good performance in the mid-band, and it was able to provide the study of different setups, because all we need to do is to connect the relevant ports of this big array. It can be, let's say, a long array, right? We just connect the ports behind this, or we can have a square array, and so on, right? So this was the reason for this. And of course, patch antennas has this sector coverage or broadside pattern, right? And this is important when you want to use an antenna for a cellular base station, because you need to define the sector, right? The cell area by the pattern of your antenna. And this antenna works well, but it is basically a conventional planar array with half-wave spacing. So people would think that, well, I mean, there is nothing really new here. Do you really have any design challenge relating to massive MIMO antennas? So channel sounder and testbed array, as the one that I showed you in the previous slide, is not for practical deployment. It does have broadside pattern for equal coverage. The antenna spacing, usually it is set to be half wavelength. Actually, that is more a phase array requirement to try to prevent spatial aliasing and high side lobes. For massive MIMO, one does not have to have half-wave spacing. In fact, more than half-wave spacing can help to increase isolation and can help to reduce correlation. So we have the need to consider robust operation, which is not really the case for this test bed and array, because it's not meant to be sitting out there in the open all the time, right? And there is the need to think about power handling. If it can take slightly more power than what a channel sounder is allowed to transmit. And more importantly, that is what I will focus on in this talk, is the oversight or size and weight of such an array. So let me give you an example. If we have a 10 by 10 array, which is single polarized, and it is working at mid-band, so let's say 3.5 gigahertz, then we can expect the size of about 0.4 and by 0.4 of a meter square. And that is not really so bad if you want to mount this on a base station tower. In fact, Ericsson has a 64 element solution, and that is shown here on the right. And this, including some radio, the total weight is 20 kilos. So here you can see that it's the mounted form. So this is fine if we only stick to mid-band, and if we only stick to, let's say, 64 or even up to 100, it's not that big yet. But if you want to go lower band, and there are reasons to go lower band. For example, you can get much better coverage area with lower frequencies. So if one really push it and let's say go down to 0.7 of gigahertz, well, LTE 700, then you are talking about an array of 10 by 10 elements of 2 by 2 meter square. Now, this is huge. If you want to put such a panel on a very high base station tower, you will have real problems, because then you will need to deal with wind load, right? You need to make a really strong, structurally strong base station, which costs a lot of money, right? And it is quite ugly to have really big stuff hanging up high in the air. So if you want to sort of get an idea of the scale, something look like this, and it will be taller than this guy. And not to mention, of course, if we need more elements than 10 by 10, and if we need more spacing, then this required space will go even more up. And this is why I call it a massive MIMO beast, because the antenna, massive MIMO antenna, can be so large, and there are at least some people who think that these antennas hanging up high, it's not very pretty, right? So we have a problem here, that we have these huge antennas that is required to give good performance for massive MIMO. So the question is, can we innovate to make this antenna smaller? Can we, in other words, tame the beast of massive MIMO? And yes, the answer is, and we have the possibility to do that if we can understand how these antennas radiate and how we can improve them. The alternative is what some would refer to as black magic. There are some very skilled antenna designers who can come out with very good antennas. Sometimes they cannot explain why they can get this antenna, but they have this intuition, right? So we call it black magic because they can do it without even understanding how it works. So I don't do black magic, I can't. So I would prefer the physical insight path. And for me, I really find the theory of characteristics modes being very useful for getting the physical insight I need to improve my antenna design for massive MIMO base station antennas. So let me start off by explaining what the theory of characteristics mode is. It basically is a technique whereby we can find the current modes of a conducting object. And these current modes are obtained from a generalized eigenvalue problem specified in terms of the imaginary and the real part of the impedance operator for this conductor object. Right? If you want to solve this in a computer, often you use a method of moments, then this will be the imaginary and the real part of the impedance matrix. So now you are able to get these current modes, right? And it has a current, it's an eigenvalue related to each mode as well. I will explain to you how we can benefit from the interpretation of these eigenvalues. But we can also find the far fields of these modes. And these far fields for different modes are orthogonal by the construction of this eigenvalue problem. So intuitive way to explain this decomposition is that we are able to find the resonance property of the conductor object. So for example, if we have a dipole antenna basically you feed it in the middle normally, and here we have just the middle being shorted, and you will see that characteristics modes can be used to explain in very simple terms how a dipole antenna operates. But of course, in reality, we use characteristics modes in structures where we don't have an intuition or do not know in advance how the resonance property is like for these structures. So for the dipole structure, you can see here, if we solve for each frequency this eigenvalue problem, we can get very many modes. But then for this structure at this frequency, because here it's in the electrically small range, we can only find one mode that is having small eigenvalues. And if you have eigenvalue of 0, that means this mode is in resonance. It is basically useful for designing antennas. So in lower frequencies, we can see only one mode can be resonant. But this mode continues to be resonant even at, or near to resonance even at higher frequency, and then more modes are coming in. Now, for the first mode, we can see that the far field pattern of this mode is like a donut, right? This is a half-wave dipole pattern. And the current distribution, as is solved by this, is according to a half-wave dipole where you have the strongest current in the middle. And then we can go on to see what the second order mode is, and that is a full-wave dipole mode where the current is strongest at these 2 points. And then the far field looks like this, and so on and so forth. You can look at the third mode as well. And the thing is, if you want to excite mode 1 only, then you will put a feed in the middle near to this resonance, so you can excite this mode and have your dipole, half-wave dipole antenna. On the other hand, you can choose to operate at a much higher frequency. Let's say at this point, you can put in a feed in the middle, and you can excite this mode now, lambda 3, but at the same time, very likely you're able to excite the first mode as well, because it still has very close to 0 eigenvalue. So now you can have 2 modes that you are using for this antenna operation at the higher frequency. So with that, let me show you how stereo characteristics modes has been used to design massive MIMO antennas. So the conventional massive MIMO antennas rely on dual polarized elements. So that means you have two broadside ports per element, and these two broadside ports are orthogonally polarized. So the innovations we can provide using stereo characteristics mode is that if we can see that there are more than two modes that are resonant on the element, then we can try to use this to design our antenna ports. So for illustration, this is a patch, right? A square patch on a ground plane. So if this square patch is small, then you can expect to have only two modes that are resonant. But if you were to increase the size of this square patch slightly, then you can see that more modes can be resonant, can be used for your antenna design. And this is the basic idea that was used in a paper published in 2016 by Dirk Manteufel's group, where he showed that he can design a 4-port element which excites simultaneously 4 resonant modes of a square plate. And he is able to use this UWB indoor MIMO purpose. And he built actually an 11 by 11 array to show that it is actually working quite well. For each of these elements here, he can show that the matching is very good and the coupling is very low. So he can get 20 dB or more isolation between the 4 ports on this array elements. And this is the 11 by 11 massive MIMO antenna prototype. So he has successfully used stereo characteristics modes to design massive MIMO elements, antenna elements with more ports. The limitation of this design is that it is broadside, it is providing broadside patterns for 2 of the ports. And it does not provide equal coverage over all ports because only these 2 ports will provide the same coverage. These other 2 ports have more monopolar light antenna patterns. So if we want to use this for the indoor scenario, which this antenna is exactly intended for, is an indoor UWB massive MIMO antenna. It is okay to do this because in indoor you have a lot of multipath and the coverage area is not well defined by your antenna pattern. So the exact shape of the pattern is not as important. But in the outdoor application, it is more important. So the question is, how do we get to broadside pattern? How do we get this pattern, sector pattern, using characteristics modes? So is it possible to do this? First, we need to get physical insight into how antenna element can radiate. To do this, we went back, me and my collaborators at the Hong Kong University of Science and Technology, went back to a paper that they have previously published on a 2-port Y-shaped patch antenna. So this is an interesting antenna, as I'll show you. When we apply characteristics mode analysis to look at this antenna, we get some ideas about how to extend this to get our 3-port elements with the same broadside pattern. Now, just to explain, this folding down here is to add capacitance, allowing the size of the patch to be smaller for a given resonance. So when we analyze the characteristics mode of this structure, we can see that there are 2 resonant modes in the desired frequency of operation. So back then, when they designed this antenna in 2001, they did not use characteristics mode analysis, but they used another approach to design the feed, which jointly excites these 2 resonant modes, but they are able to keep these 2 modes being orthogonal and uncorrelated, the 2 ports resulting from exciting these modes being uncorrelated because they are able to excite these two modes in an out-of-phase manner. So this was the way it was achieved. So looking at this antenna, of course, we understand more about how it works after we use characteristic mode analysis. But more importantly, we discover that there is a non-resonant mode that is also in this picture. Now, this non-resonant mode could potentially be used for us to get a third port, right, from our antenna element. So we went ahead and analyzed the patterns of these three modes. So mode 1 and mode 2 is what we expect. This is the broadside pattern. Mode 3 is actually a monopolar mode. So at first you think that, well, if we want to get a broadside pattern, we can't use this mode. But we decided that perhaps if we can mix out this mode in an appropriate fashion, we can perhaps still get a broadside pattern for the three ports, relying on these to give us the broadside characteristics. But the third mode is able to give us a decorrelation among the three ports. So it still plays an important role, and then we are still able to take advantage of the broadside characteristics of the modes 1 and 2. But in order to use this monopolar mode, we need to first bring it to resonance, right? Because it's not resonance yet. So we look at how the current is flowing for this mode number 3. So the current has a radially outward characteristics. So when you have these characteristics, it basically shows that it has a monopolar light property. And we know that in order to enhance this kind of behavior, first of all, we can make it into a structure with more branches, so it will support more the radially outward pattern. And then to enhance the monopole mode, a standard way to do it is to introduce shocking pin, which we have done at these positions. Furthermore, in order to lower the resonance even more for the third mode, so to bring the resonance down to where these two modes are, we can put a capacitive coupling feed, which turned out to also improve the matching as well. So with that, what used to be non-resonant, the resonance was much higher up in frequency. We managed to bring this green mode down to resonance and very close to where the other two modes are resonant. So now we have all the modes that we need, right? We have all the resonances that we need. How do we excite these resonances to make antenna ports out of them? So with this, we need to figure out how we can do that for this structure, the snowflake structure, we call it because it looks a little like snowflake. And how do we excite this? Well, we can go back to an equation that shows how the excitation of these modes and how the properties of these modes combine together to provide uncorrelated antenna ports. So this thing here is called, the alphas here are called the model weighting coefficients. So it depends on the model significance of the mode as well as how one excites these modes. And the excitation is based on putting a probe to provide high electric field, right? So for that reason, we look at the electric field just underneath this patch, and we see where are the places where we could put the probes to provide high electric fields so that we couple into the electric field of these three modes which are resonant, right? If you place them in positions where the modes have very high electric field, then the probe will feed power into these respective modes. So the other thing we need to consider is that in order to get low correlation, we need to get the correct phase properties, right? So this term here will not be providing low correlation or having values very close to 0 if you do not have opposite phase in these terms, right? If these are all of the same phase, then it will just get larger and larger, right? So we need to have some of these combinations of port locations that provide opposite phase excitation. And that is done, for example, if you look at ports 1 and 3, we have co-phase excitation in mode 1 between ports 1 and 3, and out-of-phase excitation in mode 2, and core-phase excitation for mode 3. And this allows us to get very low correlation. So with this, we have the 3-port antenna that is consisting of the top patch, and then we have this feeding plate that I explained can help us with tuning. And then we have the port locations decided by the explanation I gave in the previous slide. And what is important to notice is that we are able to use simple probe feed. We do not need to have any matching network being added to this design. And we get the resonance, the matching that we need, and also we have very nice isolation between these ports, as is predicted, because orthogonal characteristics modes are supposed to be well isolated. So this new massive MIMO antennas is being shown here, where we put 7 of these elements, right, together, and these 7 elements will give us 21 ports. And this is done so that we can see not just the coupling between the ports in one element, but how these ports in one element couple to the ports in another element. We find that the inter-element isolation is also better than 14 dB. I think here we have antenna separation of about 0.6 lambda. And just to show that it works well for actual massive MIMO regime, we have an example of 34 elements. Then we have 104 ports. And for this, we did not build a prototype, basically because it takes too much effort. There's no real need for that. But we run a MATLAB simulations where we have a rich scattering channel. And we see that the system performance is going very well. And if we have a 5 single antenna user, and we look at the uplink sum rates. So if we look at the average data rate of users going up link, and we see that both in the 21 and 102 port version, the ideal antenna and the real antenna actually can get very, both are very close to each other, meaning that these real antennas are designed very well. So it does not cause degradation in the performance, not by a lot. So one more thing I want to cover here is that we can get more insight into the coupling and correlation of this design by considering 2 things. Firstly, the intra-element diversity mechanism. How can we get very good or very low correlation when we have 3 ports which are very closely separated? Now, compared to the square patch antenna, the phase centers, when you excite these 2 ports, they are very close to each other at the center, right? So there is only polarization diversity. In this case, since you have 2 clean polarization diversity, you can get low correlation. But with the 3 ports, what is happening is that the phase centers of these 3 ports are slightly displaced from the center. And that helps a lot in reducing the correlation. The other thing to consider is that the inter-element coupling environment is different between the snowflake and the conventional design. So in the conventional design, you have 2 groups of neighboring elements. One that is rather close by, the half-wave spacing. One group that is further away, which is greater than half-wave spacing. And compared to the snowflake, we have the neighboring elements having exactly the same inter-element spacing. So this allows us to maximize the isolation between the elements, because and then we can balance this isolation for our benefit, allowing us to get better miniaturization of the array configuration. So just very quickly, I want to show you an improved design, because the original snowflake is of a very small bandwidth, so it's not so practical in real life when we want to use it to cover real cellular bands. So what we can do is to make it wider band. And what we have done here is that we recognize that this Y shape, when we change it to snowflake, it can be seen as 2 Y shapes. And because of this, we can make this having two different resonances, right? By changing the loading conditions, the length of these two Y shapes. And as being shown here, this is the current, the old design, and we can change it into this design. So by having this dual resonance snowflake consisting of two Y shapes, then from this characteristics, we can have two groups of resonances. And these two groups of resonances allowing us to have three-port antenna that is dual resonance, right? So we can have dual resonance, a wideband operation. And in order to allow us to have these two groups of resonances being close to each other so it can form a dual resonance wideband, we need to do another modification, which is just cutting this capacitive plate, which allows us to bring these two resonances closer to each other. And this is the resulting design with the split plate in the capacitive feeding plate. And then, as before, we have the possibility of using probes to feed these modes to get the three-port element design. And to do this, we follow the previous procedure, but the difference now is that we need to simultaneously excite the modes with the same feed at 3 gigahertz and another set of 3 modes at 4 gigahertz. So we need to look at the model electric field characteristics carefully to look at appropriate positions where we can do this excitation, and we can do it in an orthogonal fashion so that we can get isolated ports and low correlation. So we did that following the same design rules, and we can see again in this configuration we can find also this different core phase and out of phase excitation. So with this, we managed to design a much wider band version, and we can also verify that the ECC is very low, and we can get efficiency and gain which are quite good for the purpose in mind. And this is the prototype with the single element. And we also can show that the broadside pattern is obtained over all the frequency range within the wideband performance. And then we also show that it can work in the array configuration by making simulations of the 21 port or the 7-element version of this antenna. So I just want to conclude by saying that massive MIMO enables 5G because it really make it more practical to realize multi-user MIMO. The downside is that you need very many antennas at the base station, and to have a compact massive MIMO antenna, it's a big design challenge. So at least my group has found a very good use of the carrier characteristics modes in that it provides us insight on how to design massive MIMO antennas which are compact. And solutions, as we see it, is very competitive, is able to offer the desired characteristics, wideband, broadside pattern. And what this really is telling us is that instead of 2 ports per element, we can have 3 ports per element for about the same inter-element spacing. So we can put 50% more ports, or we can have the size of the massive MIMO array being cut down by 1/3, right? So going back to the picture of the massive MIMO being the beast, we are able to tame the massive MIMO so that the beast is now a gentleman. The size is probably now 1/3 less than the previous beast. And we can do it thanks to the theory of characteristics modes or characteristics modes analysis. I just want to conclude also by saying that there are more opportunities ahead in this field. We can do even more innovations. And in fact, I'm looking at some of these right now with my collaborators at Hong Kong University of Science and Technology. There are ways to do even more work if we can improve the theory that we are using right now for the characteristics mode analysis, and that is ongoing work. And in case any of you is interested in this technique of characteristics modes, you are welcome to consider joining the interest group that was set up many years ago by myself and a group of my colleagues who are interested in this topic. So please visit this site if you are interested. And I just want to thank again my collaborators, which has worked with me in the past few years on this work. And it's been fun working with them. And I want to acknowledge funding support from the Swedish Research Council. And thanks very much. I will be very happy to take any questions from you.
Thank you, Vincent.
Thank you.
It is always a pleasure to listen to you. And yeah, it has been quite an interesting experience for you, and a lot of things that have been done in the past few years. And there were many things that were new to me as well, some new work. So really thankful. We have a couple of questions. Like someone asked, how do we differentiate MIMO from massive MIMO? And a successive question is if there is any minimum count on antenna arrays.
You mean minimum count of the elements, right? On the
antenna. Yeah, minimum count of antennas in an array. Yeah, the elements, I guess.
A massive MIMO array.
Yeah.
So MIMO, you can still see my screen, right?
Yeah, we do.
So MIMO is a generic definition for any systems that have multiple antennas at the transmitter and multiple antennas at the receiver. Of course, for the multi-user MIMO case, then you are talking about the antennas being on different users, but they are still all receiving. So MIMO is a generic term. I mean, massive MIMO is part of MIMO scheme, right? But massive MIMO is basically a way to realize multi-user MIMO in a practical way, in a cost-effective way, or not even cost-effective. If you want to, let's say, as I presented, if you want to implement K base station antennas only to support K user, then the amount of processing that you need is very high. I'm not sure it's, I mean, you don't want to put a supercomputer in your base station. This is the motivation for having massive MIMO, because having so many antennas, what it really does is that, to give you a bit more intuition, what it really does is that by having so many more antennas, you have the possibility of making the channel more orthogonal, right? So if these two mobile stations are put much closer to each other, the channel can still be separated because you are able to use the channel with very many more elements, right? So this gives you better spatial resolution, right? This is the reason that we can take advantage of the many antennas, because it provides us this channel separability, and this is the underlying reason why we need very many antennas. It's the same as having a very large phase array as compared to a small phase array, because in that very large phase array case, you can get very narrow beam, right? If you get very narrow beam, so in the line of sight case, you can see that one beam going towards one user will not so much interfere with beam with another user, even if the user are reasonably close, right? Pencil beam, so very narrow beams. As regarding the number of elements you need, at Lund University, we would like to say that you should have at least 100 elements to get massive MIMO performance to behave well. The underlying reason is also we assume that you would like to have, let's say, up to 10 users to take advantage of this spatial division multiple access, and therefore you kind of have 10 base station antennas per user. But it gives you a general rule in getting enough spatial separability, right? So that you can get good performance with massive MIMO, approaching what you would get even if you have very few elements, but with very optimal, highly complex computational algorithms.
All right, yeah, thank you. And then we have another question that is, yeah, thank you for this interesting talk. Could you briefly introduce the energy consumption efficiency of MIMO antenna compared to the conventional antenna design?
So when I presented this slide, right, I showed that the data rate is proportionally increasing according to the number of antennas, right? So no more power is used, right? So a SISO system is using the same power as a 8x8 system here, because basically we take the same power divided by 8, right? So of course, then you will say that, well, but in order to run the RF chain, the 8 RF chain will most likely consume more power, or quite a lot more power, than one RF chain. So there is, of course, a trade-off, right? But if you have a good design of your system, you will find that it is a acceptable and a very good trade-off, right? I mean, otherwise you won't see MIMO system being used in, well, all your phones today have MIMO capability, right?
Correct. Agreed. Yeah, and I mean, from my side, mainly for IEEE young professionals, I have a question. It is non-technical, but for instance, if you have any possibilities or anything that they should be looking into, let's say if someone is new to it, they have not studied. So what is the good way to start learning about massive MIMO?
I think there is a lot of resource available on massive MIMO on the internet. There are videos that are on YouTube, some of it with multiple parts. It's very easy these days. If you type with MIMO, and you will find a lot of search results, and often the top search results would be quite reasonable. So I would say that if you want to get into this area, you can go for those. I think this this presentation, even though it's focused on the antenna, should give you a basic flavor of what massive MIMO is as well. It's only a few slides, which is really trying to explain the difference between massive MIMO and the just plain old MIMO. But if you understand these differences, that would be a very good start.
Yeah, if someone asks me, I often tell one of your early papers, the scaling up massive MIMO, the one you co-authored. I think that is also a good summary and for the beginners.
Yeah, and that paper is available on archive, so
yeah,
it's for access.
Correct. Yeah. Thank you. I think we do not have more questions, and it's just about the time. So once again, I would like to thank you for being here and for sharing your expertise with us, and hopefully we will see you again.
Thank you again.
Thank you. Bye.
Bye.